is in lenses. When light enters a more dense medium, it bends towards the normal. So for example, if we have this light ray coming in, bends towards the normal, and then bends away from the normal again as it leaves the glass. So when it enters a less dense medium, it bends away from the normal. So a lens can be thought of as a series of prisms. In this case, we've shown 5. Parallel rays of light coming from a distant object hit the prism. They bend towards the normal and then away from the normal in each of the cases. So the normal is drawn at right angles to the surface. Of course, the centre ray meets the prism at 90 degrees, so it is not refracted and passes straight through. We're going to examine lenses now, in particular convex lenses, which is the one we're looking at here, in more detail. Parallel light rays strike a convex lens. They are then refracted towards the normal, and the centre one passes straight through. These rays all converge at the focal point of the lens. So they all converge, and this is the focal point of the lens. If we were to measure from the centre of the lens to the focal point, this is the focal length of the lens. And each lens has a particular focal length, and they are manufactured to have different focal lengths. And the converse of that then, if we have diverging rays meeting the lens, they form parallel rays as they pass through the lens. So if they diverge from the focal point and meet the lens, they will then transfer as a parallel beam. If we were to investigate lenses, the focal length of a lens can be determined by focusing light from a distant object so that you have parallel rays, as shown in the previous diagram, onto a screen. So if we take the parallel rays of light from a distant object and we move the screen in and out from the lens until we get the image in focus. When we did this in the classroom, we used the light from the window and focused it through the lens onto a screen, and we measure the distance between the screen and the lens. This gives us the focal length. So the distance between the lens and the screen is the focal length. When we know the focal length of the lens, then we can carry out further experiments to determine the position of images produced of objects at different positions. Now in class we used a torch. This diagram uses a candle. If we place a torch at different positions, either beyond 2f, exactly at 2f, between 2f and f, and closer than f, we find that the image is formed at different positions on the other side of the lens, and we can capture the image on a screen. If we can capture the image on a screen, it is determined to be a real image. And in the experiments that we did in class, we were able to capture the image whenever the object was either beyond 2f, at 2f, or between 2f and f. For the experiment, whenever the object was between f and the lens, we were unable to capture it on the screen because it formed a virtual image. We are going to show ray diagrams now for each of those cases. In the first one, the object is placed at a position which is greater than 2f from the lens. Remind ourselves, what is f? F is the focal length of the lens. To draw the diagrams, there are 2 rays that we draw. The first one is we draw a ray from the very top point of the object through the centre of the lens. And we draw one continuous line. Again, remember, always use a ruler and a pencil. And we put the arrows on it to show the direction of the light rays travel. The second ray we draw is parallel to the principal axis. This line in the centre is the principal axis. And I should have told you that we show the lens itself with a double-headed arrow that's perpendicular to the principal axis. So this is the lens. Now we draw a ray parallel to the principal axis. When it meets the lens, it is refracted so that it goes through the principal focus F. So we draw a line from where it meets the lens through F and continue it on until it meets the other ray. At this point, we can then draw the image. When the object is greater than 2F away, the image is positioned between F and 2F. It is a real image. It is also inverted. By inverted, we mean upside down, and it is smaller than the object. For each of these scenarios, we have 4 statements to make. One relates to the position of the image, one relates to its nature, whether it's real or virtual, one relates to whether it's upright or inverted, and the other relates to the size. So there are always 4 points to make as a conclusion to each of these diagrams. Position, nature, whether it's upright or virtual, upright or inverted, and its size. Moving on then to where the object is between 2F and F.